Welcome to the second lecture for 162.04, Differential Equations 1. Just a quick correction from lecture 1. The equation on screen here was told to you to be the equation that an nth order ODE has to satisfy to be linear. There was a very minor error in this equation, and that is that the function on the right hand side, g of y, in fact should have been g of x. Perhaps a subtle distinction, but an important one, and that the independent variable x you can have any linear or nonlinear function on the right hand side of the equation as long as the variable is the independent variable. So we could have, for example, cosine of x, sine of x, we could have x squared, but we could not have y squared or sine of y, and so on. So sorry about that error, but moving on to what we want to cover in today's lecture. So we've got a few further definitions, explicit solutions, implicit solutions, and intervals, and also moving on to something called initial value problems. Okay, so explicit solutions. So if we have a function phi of x which satisfies the ODE in general, or normal form, and if you recall, we introduced the general or the normal form of an nth order ODE yesterday at the end of lecture 1. So if this function phi of x satisfies the ODE on some interval which we're going to call I, it's called an explicit solution to the equation on this interval. Okay, so it is possible to have functions that satisfy the ODE over a finite domain, but not maybe over the whole real line. And so we'll come across examples of that as we carry on. So the example I'd like to look at is show that phi of x, which is equal to x squared minus 1 over x, is an explicit solution to the second order linear ODE. And so the second order linear ODE, y double prime, so second derivative of y with respect to x, minus 2 over x squared times y equals 0. Okay, so we've written here that this function phi of x is an explicit solution. We want to show that. I could also write this, of course, as y of x is equal to x squared minus 1 over x. We can use either interchangeably, but sometimes it's clearer to use a different function. But we'll see what that means as we carry on. Okay, so we want to show that this function satisfies this ODE. Okay, well, if this function satisfies this ODE, then we should be able to take its second derivative, so two derivatives here. So take two derivatives of phi, and then substitute that into this equation, right? So let's do that. We'll calculate the derivatives of phi. So phi itself is x squared minus 1 over x. I'm going to assume that you're quite comfortable with taking derivatives. If we take the derivative of x squared, we get 2x. If we take the derivative of minus 1 over x, we get positive 1 over x squared. And then, of course, we need a second derivative. So if we take the derivative of this function, the derivative of 2x is just 2. And the derivative of 1 over x squared is simply minus 2 over x cubed. Okay, and we're going to use these expressions in the ODE. So phi double prime we're going to put in place of y double prime, and phi we're going to put in place of y. So if we do that, we get, well, y double prime, or phi double prime is 2 minus 2 over x cubed. So we've got 2 minus 2 over x cubed here, minus 2 over x squared, times y, or in this case phi. So x squared minus 1 over x, you can see here x squared minus 1 over x. Okay, and we want to show that that left hand side is equal to 0. Okay, so we can simplify this, right? We can say, well, 2 minus 2 over x cubed is the same. Well, that doesn't simplify. But here we can take this product into the brackets, right? So 2 over x squared times x squared is just going to be 2. you see the x squareds are going to cancel here to make 1. And minus 2 over x squared times minus 1 over x is going to make positive 2 over x cubed. Okay? And so you can see here that we're going to get a 2 minus a 2 and a minus 2 over x cubed plus a 2 over x cubed. So these things are going to cancel out nicely. So this left hand side is 0, this right hand side is 0. So we can say with confidence that x squared minus 1 over x is an explicit solution to this ODE. So again, sometimes we'll write 5x equals x squared minus 1 over x, but it's legitimate to write y of x is equal to x squared minus 1 over x and say that that is an explicit solution. Okay, so I just say here that 5x is a solution to the ODE for x not equal to 0. So this is important. So if you look at what happens here, if I substitute in x equals 0 into this solution here, well, it's actually undefined, right? Because we'd have something that's 1 over 0. So in fact, our solution is only valid on any interval that does not contain the point x equals 0. So we can't touch that point x equals 0. We can go close to it, but we can't touch it. Okay, so therefore we say y of x now. I've switched to y of x from 5x. Both are interchangeable. So y of x is equal to x squared minus 1 over x is an explicit solution to the ODE on the intervals minus infinity to 0. So note the use of the rounded brackets, which tells us that we're not including the point. So we're not including minus infinity or 0 here. There will be other times where we have a square bracket, which means we would include the number. But anyway, we have an explicit solution on the intervals negative infinity to 0 and 0 to infinity. So not including the point 0. Okay, so that interval I was talking about here, so it's got multiple names depending on which textbook you look at, but it's sometimes called the interval of definition, or the interval of existence, the domain of the solution. It is basically where the solution 5x and its n derivatives exist, or in other words, where they're finite or defined. So anywhere where the solution is not going off to infinity. Anywhere that, for example, if you had a log of x in the solution, you could never have x that was negative, right? Because log is not defined, or even equal to 0, right? You can never have x 0 or less. So we'll have to keep this in mind whenever we find solutions to our ODEs. Where is the solution defined? What is the interval of existence of the solution? Okay, so we looked at explicit solutions where we could write y of x is equal to some function of x. But sometimes that's not possible. So we have something called implicit solutions. Okay, so we have some function which I'm calling g here, which is a function of two variables, x and y, equal to 0. And it's said that this is an implicit solution to the ODE on the interval I if it defines one or more explicit solutions on I. So what does that mean? Well, let's look at by means of example. So we're asked to show that x plus y plus e to the xy equals 0 is an implicit solution for the first order nonlinear ODE given here. So there's a few things I'd really like to point out here. So this is a first order nonlinear ODE. Now if you recall, why is this a nonlinear ODE? Well, we learned this last time. dy by dx is okay, there's nothing wrong with that, but we're multiplying dy by dx, the first derivative, by e to the xy. Okay, and so this term here, and in fact this term too, e to the xy over here, makes this a nonlinear ODE. Remember, y here is going to be the dependent variable, x is the independent variable. Okay, and so the reason that this solution in equation 1 here has to be an implicit solution there is no way to rearrange this equation here, equation 1, to make y the subject of the formula. You cannot write y is equal to some function of x. You're always going to have these x and y intertwined here because of this exponential term, in fact. Okay, so this is going to be an implicit solution because we can't write this as y equals some function of x. Okay, well, let's see if this is in fact a solution to this ODE. So, okay, well, this is already what is something I've already said. Let's let this function g of xy be equal to our thing that we're testing to see if it's an implicit solution. So let's let g of xy equal x plus y plus e to the xy. So this equation 1 here. Okay, and we can use implicit differentiation to find the derivatives of g, because remember, y is a function of x, because y is the dependent variable and x is the independent variable. So if we're taking the derivative of g here with respect to x, we need to remember that y itself is a function of x. Okay, so I've just rewritten this page to make it a little, give myself a little bit more space. So we've got equation 1, which is the test solution. We've got the ODE itself, and we're saying g of x is equal to this thing. If we take the derivative of g of x with respect to x, that's the same as taking the derivative with respect to x of this function here. So, okay, if we do this term by term, d by dx of x is, of course, just 1, because x is a polynomial of order 1. So the derivative of x just becomes 1. The derivative of y becomes, with respect to x, just becomes dy by dx, right? This last term here is a little bit trickier because we have to use the chain and product rules. Right? So, again, this what we saw before was dy by dx of x is 1, and dy by dx is dy by dx. And so here, this last term, we have to use the chain and the product rules. Okay. So if we first take the derivative with respect to x here, because we got the product here, if we first take the derivative with respect to x, the derivative of e to the xy is going to be simply equal to, we're going to have a y up the front here, so we take the derivative of the exponent, so we get y times e to the xy. So we get y times e to the xy. By the product rule, then we're going to sum, we're going to add the next term. So we're going to take the derivative of this thing, keeping basically this y constant, and then which basically gives us, if we take the derivative keeping y constant, we get an x out the front times e to the xy. But we also have to use the chain rule too, right? So then we take the derivative of the y, which is dy by dx. Okay, so this is well, quite a lot of differentiation rules from first year calculus. We're using implicit differentiation for one, and we have to also use the chain and the product rule on this last term here. Okay, so it's probably worth taking a minute to make sure that you're comfortable with all those three ideas, those three concepts from first year calculus. It's a good reminder to revise, which I always have to do. Okay, well, that was the derivative. We can define the derivative of g, this function g with respect to x, but recall that g itself was this thing, and we were saying that that has to be equal to 0, or effectively equation 1. This thing on the left hand side is g, that has to be equal to 0. So if we take the derivative of g, the left hand side, and we get this, we also have to take the derivative of the right hand side, right? Okay, well, it's particularly easy because the derivative of 0 is just 0. So we end up saying that this implicit derivative of g has to be equal to 0. Okay, so see, we have our 1 plus dy dx plus e to the xy, y plus x dy dx, y plus x dy dx. That thing has to be equal to 0. Okay, you can easily rearrange this to show that this matches equation 2 up the top here, our ODE, our first order nonlinear ODE. And you can see that because if you just look at the dy by dx terms, well, we have 1 here, and over here we have e to the xy times x, lots of them. Okay, so we're going to have 1 plus x e to the xy, 1 plus e to the xy times dy dx. And then we're going to, for the y terms, so the terms that are multiplied by y, we're going to have simply an e to the xy, and then for the constant terms, we've just got simply a 1 over here. So it's not too hard to see that this equation is just a rearranged form of equation 2. So therefore, we've shown that our function in equation 1, or our equation 1 here, is an implicit solution to the ODE 2. The point is really that you can't always write a nice, neat, happy solution to an ODE. You can't always write y is equal to some function of x. Sometimes you have some equation that you cannot make y the subject of the unique subject of the formula. And so therefore we have implicit solutions. Okay, so moving on to another definition now. And so this is again one of the more practical parts of differential equations, called initial value problems, or for short IVPs. So again, mathematicians, we really love to shorten words because, well, we're pretty lazy. We don't like writing out too many words if we don't have to. So there's a lot of short definitions that you have to learn. For example, ordinary differential equation is an ODE. Partial differential equation is a PDE. A differential equation is a DE. And initial value problems is an IVP. Okay, so an IVP, or initial value problem, is very simply an ODE, or in fact it could be PDE as well, but okay, we're going to deal with ODEs here. An ODE, so here we have an nth order ODE. So an ODE combined with some initial conditions, okay? And in fact, it has to be a very specific number of initial conditions. Okay, so how do I know, or why do I call these initial conditions? Well, x naught here, x naught is some number in the interval where this ODE is defined. Okay, often that's 0. Okay, so often the point x naught is equal to 0 in a lot of the applications we're going to be looking at. And so what we're saying is that we have this nice nth order ODE. This is in the normal form of the ODE. Okay, we also have to have n constants called initial conditions. So here we have the value of y at some number x naught is equal to some number y naught. The value of the derivative of y at the same point x naught, where x naught is just some number in the interval, is equal to some number y1, and so on through to the n minus first derivative of y at this point x naught has to be equal to some number yn minus 1. Okay, these are called the initial conditions, these the right hand sides here. So if we simply had the ODE here, this would just be an nth order ODE. When we combine the ODE with some initial, the right number of initial conditions, then this becomes what's called an initial value problem. Okay, and this is crucial to solve practical systems or practical applications of ODEs. So we need one initial condition for each order of the ODE. Here, as you might have figured that out already. So for example, a first order initial value problem consists of a first order ODE, or in our case ODE. So dy by dx, one derivative, is equal to some function of x and y. So we have so this first order IVP has this first order ODE and one initial condition. So first order, one initial condition. So we say take some point x naught in the interval of definition of our ODE and say we know that at this point this is the value of y is equal to y naught some number. We'll look at an example shortly. Or if we have a second order initial value problem, so we say the second derivative of y with respect to x is equal to some function of x, y, and the first derivative of y. For this ODE to become an initial value problem, we need to supplement it with two initial conditions because we have a second order ODE. And so here we have an initial condition on y and an initial condition on y prime, so the first derivative of y. So the point is, for an ODE to become an initial value problem, you need to give it the right number of initial conditions. It's a subtle difference, but one that's important to get your head around for this class. So let's look at an example. So I'm throwing text at you here. So we're going to consider the following second order linear ODE. Okay, well it's second order, so we already know this ODE is second order, so we already know that for it to be an initial value problem, we're going to at some stage need two initial conditions. So the second derivative of y with respect to x minus the first derivative of y with respect to x minus 2y equals 0. So firstly we want to show that this function phi of x equals c1 e to the minus x plus c2 e to the 2x, where c1 and c2 are some numbers. We want to show that this is a solution to the ODE. Okay. We call this a two-parameter family of solutions because we got two parameters. C1 and C2 are some numbers that we don't know yet. So we say it's a two-parameter family of solutions. And the solution will look quite different depending on the value of those two numbers, right? C1 and C2. Okay, so firstly we want to show that that's the solution to start with. And secondly, we want to determine these numbers C1 and C2 so that the initial conditions are satisfied. Y, when x is equal to 0, y is equal to 2. When x is equal to 0, the derivative of y is equal to negative 3. Okay, so this ODE combined with these two initial conditions form an initial value problem. Okay, well, let's start with part A. Here is our ODE at the top. Here is our function that we're saying satisfies the ODE, and here is our initial conditions, right? So to show that this function satisfies the ODE, we better calculate some derivatives. Okay, so you'll notice in the ODE we need a first and a second derivative. So if we take the derivative of phi, well, it's quite nice because taking the derivative of exponentials is very easy. We're just simply going to get phi prime, the derivative of phi with respect to x is equal to negative c1 e to the negative x plus 2 c2 e to the 2x. So the 2 here comes from the exponential 2x. And again, we can play the same game and take a second derivative, right? It's quite straightforward. And so now we want to use these three functions, phi, phi prime, and phi double prime, in the original ODE. Okay, so if I do that, well, I get phi double prime is c1 e to the minus x, c1 e to the minus x, plus 4 c2 e to the 2x. We take away dy by dx, so we take away phi prime. You can notice that this line here, phi prime, matches this line here. And then we take away 2 times y, so we take away 2 times phi here. And hopefully you can see that these things easily cancel out to be 0. This left-hand side cancels out to be 0. We get c1 lots of e to the negative x. We get plus c1 e to the negative x here again, so that's 2 c1 e to the negative x. But then we subtract 2 c1 e to the negative x here, and similarly for the other terms as well. So you might like to convince yourself that that left-hand side does actually cancel out to be equal to 0. And since that is the case, phi is an explicit solution to the ODE. Another thing to point out is that phi and its derivatives are finite and defined on the interval negative infinity to infinity for any values of c1 and c2, right? So exponentials don't blow up to infinity for any finite value right? So e to the 2x doesn't become infinite until x becomes infinite. There's no funny points we have to watch out for. Okay, so we know that phi now is a solution to the ODE. So now we've got to look at our initial conditions to try and figure out what these values of C1 and C2 are. The first initial condition, when x is equal to 0, y is equal to 2. Okay, what we're going to do is just substitute x equal to 0 into this solution phi. Okay, so if I do that, phi of 0, when x equals 0, we get C1 times e to the negative 0, C1 e to the negative 0, plus C2 e to the 0. And as we know, e to the 0 is just simply equal to 1. If you put that in your calculator, you can convince yourself that e to the 0 is equal to 1. Okay, and so we know that this thing, when we substitute x equal to 0, we know y is equal to 2, right? So we know that C1 times e to the negative 0 plus C2 times e to the 0 is equal to 2. Therefore, we can simplify that a little bit and show that C1 plus C2 is equal to 2. Okay, that's good. We can't tell you the value of C1 and C2 yet, but we know that if we add C1 and C2 together, we get 2. Okay, but I can say, well, let's look at our second initial condition now. So our initial condition on y prime. So we know that y prime, when x equals 0, y prime is equal to negative 3. Okay, so remember here is y prime, well, it's phi prime. So let's substitute x equal to 0 into this derivative, so phi prime, and see what we get. Okay, well here we get, again, the exponentials become e to the 0, or in other words 1. So here basically what we get is negative c1 plus 2c2 is equal to negative 3, which is the second initial condition here. So negative c1 plus 2c2 is equal to negative 3. Now if I combine these, if I write these two expressions for the constants next to each other, so c1 plus c2 equals 2, negative c1 plus 2c2 equals negative 3, we get two simultaneous equations that we need to solve for c1 and c2. And of course there are multiple methods of solving these simultaneous equations, but I'm just quite simply going to rearrange the first one, so what I'm calling I here, to make c1 the subject of the formula. So if I take c2 away from both sides of the equation I here, I get c1 equals 2 minus c2. And I'm going to use this expression in the second equation. Okay, so wherever I see a c1 in the second equation, which is only here, I'm going to write 2 minus c2. Okay, so here's my 2 minus c2 plus the other 2c2 equals negative 3. And quite simply, I can solve this for c2 now. If I add 2 to both sides, I'm going to get 3c2 equals negative 1. So c2 is going to be negative 1 over 3. c2 is negative 1 over 3, and I can also show c1 is equal to 7 over 3. Because c1 is just 2 minus c2. So if c2 is negative 1 over 3, we get 2 plus 1/3, which you can hopefully see that these are the solutions to their system of equations. Feel free to double check my working and substitute these numbers into these two equations, I and double I. So therefore, this solution phi now, we can tell you what the numbers c1 and c2 are. So c1 is 7 over 3, so phi of x is equal to 7 over 3 e to the minus x plus negative 1/3 e to the 2x. Okay, maybe if I can just be a little bit clear and maybe labor on this point a little bit longer, phi of x is a solution to the ODE, the second order ODE given here. Okay, phi of x is a solution to the second order ODE. It's a two-parameter family of solutions, in fact, to this ODE. The phi of x we've just found down the bottom here, 7 over 3 e to the minus x plus negative 1/3 e to the 2x, is a solution to the initial value problem. So there's two separate things here. We've got the solution to the initial value problem, which consists of the ODE plus the initial conditions, and we've also got the solution to the ODE itself if there were no initial conditions, so to speak. So It's an important difference, and hopefully I'll try to labour that point as we move through the class. So that's all for today. I look forward to seeing you in Lecture 3. Thank you.